Okay, so just to warn you in advance, I will briefly stick my head out in about 10 or 15 minutes because I have a student finishing at my camp, but that'll just be a slight interruption. So last time we saw telescoping series are the second of three types of series that we can actually hope to evaluate exactly. And the one example we did seemed like it required inordinate doses of clever. You had to just sort of notice that these fractions could be cleverly rewritten in certain ways. So the first thing for today is to talk a little bit more systematically about how you can do telescoping series. And it turns out that there's a connection with partial fractions, which we haven't seen for quite a while, but here they are popping up again. As an example, let's suppose I wanted to find the sum from, say, n equals 3 to infinity of 1 over n squared minus 4. I'm starting this sum at 3 because when n equals 2, we're dividing by 0, and it wouldn't make any sense. So we'll just start it later, so all the terms exist. So I could compute a few terms here. 1/5, that's 9 minus 4, plus 1 over 16 minus 4, plus 1 over 25 minus 4, and so on. If I started here, I would need to do some work to get here, but a sort of plain vanilla version where I'm not making you be crazy clever, I'll give you a formula like this. So you don't have to notice the pattern in the denominator. Just have to figure out what to do. Well, of course, continuing our n-x relationship, if this were 1 over x squared minus 4, we have this whole machinery to rewrite it with partial fractions. Same machinery works here. So partial fractions, I'll just go through the whole procedure using n rather than x. Doesn't make any difference. 1 over n plus 2 n minus 2. Back to that difference of squares. According to our partial fractions theory, that should be some constant over n plus 2 plus some other constant over n minus 2. So we just need to find those coefficients, same as in week 4 or whatever it was. So we multiply by this to clear denominators. Here, n plus 2 over n plus 2 cancels. I have a times n minus 2. And here, the n minus 2's cancel. I have n plus 2. What next? Anybody remember from like 6 weeks ago? Hi? Great, so we're going to evaluate both sides at n equals 2, evaluate both sides at n equals minus 2. So at n equals 2, this equation says that 1 equals, that's a times 0 plus b times 4. So really b is a fourth. And at n equals minus 2, this equation says that 1 equals negative 4a plus 0b, so a is negative 4. And so what we conclude from our partial fractions work is that 1 over n squared minus 4 is the same as negative a fourth over n plus 2 plus a fourth over n minus 2. That was the point of that little description. Okay, well, then we need to see what that's going to do for infinite series. So over here, I know that this infinite series can be rewritten as the sum from n equals 3 to infinity of, just that expression there. I'll put it inside parentheses. So negative a fourth over n plus 2 plus a fourth over n minus 2. Now, it may not be obvious at this point that the series is even telescoping. I've just rewritten it in a different way. But probably easiest to see if I write out the first few terms. I'm going to pull out the common factor of a fourth as a small step to simplify life. And I'll rewrite the order of the terms. So I'm doing 1 over n minus 2 minus 1 over n plus 2. So let's compute a few and see what the pattern is, right? Starting with n equals 3, and then the n equals 4 term, and then the n equals 5 term, and so on. So for n equals 3, I have 1 over 3 minus 2 minus 1 over 3 plus 2. For n equals 4, got 1 over 4 minus 2, 1 over 4 plus 2, and so on. This one, the telescoping, is a little bit more complicated than last time. The cancellation is delayed a little bit more. But we can see that, for instance, this negative a fifth cancels with this positive a fifth. If I were to go out, maybe I'll go one more turn. This negative a sixth cancels with this positive a sixth, and so on. So once I go far enough out into the series, my terms are going to start canceling. There's actually several initial terms that don't cancel this time. Right? If I look for the terms that are left, 1, a half, a third, and a fourth all survive the cancellation. Last time we just had the one initial term that survived the cancellation. All 4 of these don't cancel, but then starting with a fifth, right, everything cancels. This and this, this and this, and so on. So when I take the sum, I get all the surviving terms, all the ones that don't cancel, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. I could put that over a common denominator. I'm not going to bother. This is the infinite sum. I'll just have a brief word about what would happen if I did a careful version. And we said that, if you want to really dot the i's and cross the t's, we need to find a formula for the nth partial sum. Because we want to avoid the kind of shady business that we did on the first day. If we were to take any finite partial sum, go from n equals 3 to 17 or whatever, we'd have 4 terms that survive at the beginning, and they'd be balanced by 4 terms that survive at the end. If I did the sum from n equals 3 to 17, my surviving minus terms are going to be like 19, 20, 21, and 22. And those 4 subtracted terms balance out the 4 additive terms. But as the number of my partial sum goes to infinity, the 4 subtracted terms are all going to 0. So we're 1 over 1,000,002, 1 over 1,000,003, 1 over 1,004, 1 over 1,005. So in the limit, those all die off. these terms are one. All right, so the type of telescoping series that you should be ready to do, if I have a rational function, you can expand it in a partial fraction expansion. Write out a few terms so you can see the pattern and figure out what doesn't cancel. Right? And that's your infinite sum, the stuff that doesn't cancel. Okay. Since we're moving on to a new section, this is the time we'll let that go briefly. In a few seconds. All right, so earlier, we talked about the fact that most series you can't evaluate exactly. Right? So we've spent some time on the exceptional cases, geometric series, telescoping. But most of the time, there's no hope of getting an exact answer. And so one of the big questions becomes, does the series even converge? So we're going to have this whole battery of tests that we'll develop to test that. So in the big picture, we'll develop many convergence tests. So implicit in that, there's something of an art to figuring out which ones to use when. Right? Which kind of series can you analyze with which test? Any given test can be inconclusive sometimes. So the closest thing we've seen so far was using the comparison theorem on integrals. And we saw that 2 times out of 4, the comparison theorem doesn't tell you anything. If you have something that's bigger than a divergent integral, you know it diverges, but if it's smaller than a divergent integral, you don't know anything. Okay? So all of our convergence tests for series will sometimes just not tell us what happens. So then you try another test. So we'll have to be careful about the direction of the logic, if A then B versus if B then A. So we'll see our first couple of tests probably today, and they'll be on the quiz tomorrow. And then the next week to 2 weeks probably, we'll just be learning and applying a variety of convergence tests. All right. The first test is named the divergence test. And that's a hint for what it can and can't tell you. This test will never prove to you that anything converges, but it can prove to you that something diverges. Hence, it's called the divergence test. And the statement is just you look at whether the terms go to 0. So the theorem is if the sum of some terms converges, then the terms go to 0. All right, so one other minor point that I could make in general, it doesn't really matter where you start. I sort of mentioned before that sometimes we start at 0, sometimes we start at 1. Actually, on the web work, you probably saw some sums that start at n equals 3 or n equals 7 or whatever. In terms of convergence, I'll put this over here in the generic comments. Whether or not a series converges is unaffected if you ignore several terms, right? So, if I do something like the sum of n equals 0 to infinity converges if and only if, for example, the sum from n equals 17 to infinity of an converges. The difference between this series and this is just some number, the sum of the first 16 terms. That's not going to be infinite. So if these partial sums approach a limit, these approach the same limit minus that number, and vice versa. So convergence is only ever affected by sort of the trends at infinity. The first couple of terms have no bearing on convergence. All right, so this theorem would be equally true if the sum from n equals 42 to infinity converges and the terms go to 0. Right? It doesn't. All right, but let's just say starting with 0. So if the sum converges, the limit is 0. The proof. This is going to look a little bit clever, but each term is a difference of two partial sums. An is the nth partial sum minus the n minus first partial sum. Right? This is like a0 plus a1 plus a2 dot 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 plus an. This subtracts out all the terms except an. So suppose the series converges, which means the partial sums approach a limit, i.e. the series converges. Then an has to approach L minus L because it's a difference of two things that are approaching L. All right, so if the series converges, the terms go to 0. This is logically equivalent. So, contrapositively, if the terms do not go to 0, then the series does not converge. This is the form that we'll actually use most of the time. So as a side point on logic, if A then B is logically equivalent to if B then A. Oh, sorry, that's not true. If not B, then not A. These two statements are said to be contrapositives of each other, and contrapositives have the same meaning. They're asserting the same thing. So if converged, then limit 0, contrapositive. If not, limit 0, not converged. So this is why it's called a divergence test. Right? You can look at the terms and conclude that the series diverges. So an easy example that we've already seen several times now. Take a series like this that diverges. Last time, or the time before, I think it was last time, we proved this by looking at the partial sums. The partial sums go 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4. we have this pattern in the partial sums. We can use that pattern to prove divergence. But we can actually prove divergence much more quickly. We don't have to find the nth partial sum. All we got to do is say, well, the terms aren't going to zero. Boom. Divergent. This is basically always the first thing that you should check. So, put a pin in this as we go through, 8 different tests or whatever. You always start with this one. You're given a new infinite series to sight read. The first question you ask yourself is, do the terms go to 0? And if the answer is no, you're done. And it's usually quick and easy to tell. All right, so let's do a few examples of how you could apply the divergence test. I'm actually going to tie this in with some of our sequence practice. So right, the day before our last quiz, we printed out a page from the book and said, here's 40 different sequence problems. Let's find their limits. We could turn that into 40 different series problems and apply the divergence test. Right, so what if I take the sum from 1 to infinity of natural log 2n plus 1 over 3n plus 4. So a week ago, we did this without the sum, and we just asked what's the limit of that sequence. Now we're going to turn it into a summation problem. So the question at hand is, do these terms go to 0 or not? I'd be hard-pressed to find an expression for the nth partial sum. But a much easier question is just a sequence limit. Do the terms go to 0? What do you think? Remember how to do this one as a sequence problem? Good?
It would end up going to 2/3. It would be n over n.
Yeah, or the natural log of 2/3, right? You're sort of doing the composition here. Yeah, so the limit as n goes to infinity of natural log 2n plus 1 over 3n plus 4 is the log of the limit. That's the composition theorem for sequences. This limit you can do with L'Hopital. You can do by just comparing these leading terms which have the same degree. Whichever way you prefer to do that, it's natural log 2/3. For our purposes, the important thing about natural log 2/3 is it's not 0. The natural log of 1 is 0. The natural log of 2/3 is not 0. So this series diverges because its terms don't go to 0. Let's do another one. So again, this is straight off the page on limits of sequences. I'm just going to turn my sequence problem into a series problem. And the question that we need to address is, do these terms go to 0? What is the limit as n goes to infinity of 8 to the n over n factorial? How do we do that?
We know factorials grow the fastest. You know they grow faster than exponentials.
Right. So the bottom's growing faster than the top. The sequence goes to 0. So this is by our rates of growth hierarchy. factorials aren't the absolute apex predator, n to the n is even bigger, but of these two, and those are certainly faster than an exponential. So the terms go to 0. What can we conclude about the series?
It doesn't diverge.
Say what?
It doesn't diverge.
Not quite. What we can conclude is we don't know that it diverges. It isn't, so this, maybe not. This is the case where the divergence test is inconclusive. So if the limit of your sequence is 0, the divergence test doesn't tell you anything. So applying the divergence test, check whether terms go to 0. If no, then the series diverges. And if yes, then the divergence test is inconclusive. And so you need to try to pull another tool out of your toolbox and see what happens. As we go through the theory of series, we'll be able to come back to this one in a couple different ways. So later, we'll develop something called the ratio test that will tell us that this series converges. And then later still, we'll be able to use Taylor's series to find the value. In fact, the value of that series is e to the 8th power. But we're not there yet. The divergence test tells us that maybe that series converges and maybe it doesn't. It doesn't tell us anything. In the bigger picture, most of the series we're looking at, the terms will go to 0. So most of the time, the divergence test is not going to answer a question for us. Think of it as filtering out the really easy cases, right? It takes care of the series that don't even have a chance. Suppose you were a scout for a Major League Baseball draft, and you go and look at a field, and you find that one of the players can't even throw a ball 10 feet. Okay, cool. So look at the other ones. But it's not a very powerful test, right? Most of what you want to know is not going to tell you. So most of the time we'll be relying on tests. Okay, so the next actually set of tests, we'll probably just work on one of them today, are specific to positive theories. If we assume that all the terms in our series are positive, there are some questions that become simpler. For positive series, there's only 2 possible outcomes instead of 4. So if I have a sum and all the terms are positive, it either converges or it diverges to infinity. Meaning the partial sums become bigger and bigger and bigger without any upper bound. You can't, of course, have the sum diverge to minus infinity if there's no minus. You also can't have this kind of oscillatory behavior. Like when we look at sums like 1 minus 1 plus 1 minus 1 plus 1 minus 1, that series is tricky because it bounces back and forth. You can't do that if you're just adding. The partial sums are growing. The question is, do they grow towards some fixed number or do they grow to infinity? Those are the only options on the table. So certain types of analysis will be simpler if we add this assumption of positivity. Later, when we come back to series where the terms could have both signs, we'll actually use some of this theory to help in that more general case. So this is a step towards general series. So we're going to have about 3 or 4 different tests that are just for positive series. The first we'll look at today. The others we'll get to after the quiz. First one is not really a test, but kind of a preliminary for the tests. So this one, I'll just call it Theorem 10.3.1. It's related to this observation here about only having 2 possibilities. If all the ANs are positive, then the sum converges if and only if the partial sums have an upper bound. So suppose I had a series of positive terms. Right? So I was adding, getting more and more and more. Suppose I told you all the partial sums are less than 1,000,000. That wouldn't mean that the series added up to 1,000,000. Maybe it adds up to 5. But if all the partial sums are less than 1,000,000, the series can't diverge to infinity. So then it would have to converge. Those are the only 2 options. So when we're dealing with positive series, the question of convergence is equivalent to the question of, is there any upper bound at all on how big these partial sums can be? We will mostly keep this in our back pocket as we develop the other tests, but I want to show you one important example where this insight can already tell us directly whether it converges or not. So the one example where we'll apply this theorem directly, but I'm not going to require you guys to apply this theorem directly. Right? So you should know the example I'm about to give, and then we'll move into the next step. The example is a harmonic series. So 1 plus a half plus a third plus a fourth plus a fifth. That series diverges. And we're going to prove it by showing that the partial sums become bigger than any fixed number. The trick is, I'm not going to look at every partial sum, just some of them. It is A1, A2, A3. I'm going to look at the first, second, fourth, 8th, 16th, and so on partial sums. I'm just going to focus on the ones that are powers of 2. We'll see why. The first partial sum is 1, and the next is 1 plus a half. If I look at S4, I'm adding up these 4 terms, and rather than evaluating that exactly, I'm going to say that's bigger than 1 plus a half plus a fourth plus a fourth. Because, after all, a third is bigger than a fourth, right? This is bigger than that. So my fourth partial sum is bigger than 1 plus a half bigger than 2. What about the eighth partial sum? Well, I can round these down to a fourth, and I can round all of these down to an eighth. A fifth is bigger than an eighth, and a sixth is bigger than an eighth, and a seventh is bigger than an eighth, and an eighth is bigger than or equal to an eighth. This whole thing is bigger than 1 plus a half plus 2 terms, each of which was at least a fourth, plus 4 terms, each of which was at least an eighth. That's 1 plus a half plus a half plus a half, that's 2 and a half. Similarly, S16 turns out to be bigger than 3. There are 2 terms that are at least a fourth, 4 terms that are at least an eighth, 8 terms that are at least a 16th, and so on. So when I look at these power of 2 partial sums, I find one that's at least bigger than 2, another one's bigger than 2 and a half, another one's bigger than 3, another one's bigger than 3 and a half, another one's bigger than 4. If I go far enough out, I can find one that I'm guaranteed is bigger than a billion. If I go far enough out, I can find one that I know is bigger than a trillion. There's no upper bound on the partial sums. Right? They eventually outgrow any target. So because there's no upper bound, the series has to measure. All right, so and this is a kind of a tricky analysis here. This theorem is difficult to apply directly, but it powers some things that are a lot easier to use. The first of which is the integral test. So this will be the last technique on tomorrow's quiz. The integral test applies to a function that satisfies 3 criteria. Well, mostly 2. Positive, decreasing, and continuous. It's rare that we'll have to worry about continuity. Integral test says then the series that you get by adding up the function, so f of 1 plus f of 2 plus dot dot dot, converges if and only if the integral converges. So this allows us to use our integration skills, which we spent like a month building, right, to determine the convergence of series. One of the features that you should notice in as different from the divergence test. This is a two-way street. You can use the integral test to prove convergence, and you can use the integral test to prove divergence, either one. I'll explain next time why the integral test is true, but since we just have 10 minutes to go, I'll illustrate how to use it, and you can practice that on the whiteboard and be ready to do it tomorrow. So we'll postpone, proof. It's really cool. There's a nice picture. Looking forward to it. But let's look at some examples. Does the sum from n equals 1 to infinity of 1 over n squared converge? So that's 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and so on. 1 plus a fourth plus a ninth plus a 16th. Converge or diverge? So to apply the integral test, I'm going to look at this and say that's some function of n. F of n is 1 over n squared. Looking a lot like the sampling theorem here, the corresponding function f of x is 1 over x. So I need to check that the criteria are satisfied for the theorem to work. Is positive, check. 1 over x squared is positive. Continuous, yes. I'm not worried, by the way, about it blowing up at 0. I'm only worried about what happens from 1 to infinity. That's the region where I'm summing. That's the region where I'm integrating. What happens at 0 doesn't really matter. So continuous, right, positive, and then decreasing. I could check the derivative, but again, I can also just use a shortcut of saying the bigger a number is, the bigger the square. Right? The bigger the denominator, the smaller the fraction. Right? So if x gets bigger, the fraction gets smaller. Yep, that's a decreasing function. Cool. So the integral test applies. All right, well, what the integral test says is I can answer my convergence question by doing an improper integral. So what if I integrate 1 over x squared out to infinity? You may remember the punchline because we looked at this class of examples where I have a power of x. But suppose you forgot the answer, you can just do this from scratch. Take the antiderivative, plug in the endpoints, negative 1 over infinity minus 1 over 1. The integral is 1. The most important thing about 1 is it's not infinity. So that improper integral converges. And what we'll say is by the integral test, the sum of 1 over n squared converges too. Yeah, there.
Could you use this if it was negative and increasing?
Who would say what? Negative and increasing?
Yeah.
Yes. Good. Yeah. If we had a series of negative terms, then we converge if and only if the negative of it converge. And the integral test would apply there. Yeah. Right. Now, there's nothing special about 2. We could generalize this example to 1 over powers of n. So similarly, the integral test implies that if I take a series of this form, converges if and only if p is greater than 1. A series of this type is sometimes called a p-series. We just looked at a p-series with p equals 2. The harmonic series is a p-series with p equals 1. Right? The harmonic series diverges. We could have also proved that with the integral test, if we hadn't done it straight from the partial sums. The integral test would give us a log of infinity. P doesn't have to be an integer here. If I took 1 over the square root of n, that's p to the 1/2, it diverges. If I take 1 over n to the 1.3, it converges. So any positive number you can put in here, the integral test will give you the answer. Let's look at one more example of the integral test. Practice it on the homework. Does the sum from n equals 1 to infinity of 1 over n natural log n converge? Actually, just realized this would be the division by 0 if I started at 1. All right, small technicality. All right. So, positive? Yes. Natural logs of 2 and above are positive. N is positive. Continuous? Yes. And decreasing, again, I'm going to use this kind of shortcut. If n gets bigger, this gets bigger, and this gets bigger, so the product gets bigger, so the fraction gets smaller. Right? Or I can take a derivative. All right, so the integral test applies. So I'm going to turn n into x. And now I have to figure out what to do with this. 1 over x natural log x. It's a little bit more work required than the last one. Maybe you can't just write down an antiderivative, but what could we do using our bundle of integration techniques? Excellent.
Could you use substitution?
Yeah, what are you thinking for u?
1 over x?
I'd rather do log, although you're on the right track. So if I do u equals log x, du is 1 over x dx. And then if x goes from 1 to infinity, u goes from the log of 1 to the log of infinity. This is 1 over u du. That actually blows up on both ends. Right? It blows up here because of a 1 over 0, and it blows up here because of a log of infinity. So, but by the way, if you write an antiderivative here in terms of x, it's log of x. The integral, this is log of x. But that infinity blows up.
Weren't we starting at 2?
Oh, yeah, good point. That fixes that problem. Yes, thank you. Yeah, so the integral diverges, right? You sort of get the log of infinity, which is still infinity. Thus, the original sum of 1 over n natural log n diverges to. So one of the things we're going to start thinking about if you're given a series, we have several things to try now. Right? If you're just given a series and ask what happens, you could notice that it's geometric. You might be able to figure out that it telescopes by doing a partial fraction. You want to look at the terms and see if they go to 0. But you also want to think, if I turned n into x, could I integrate this? And anything's open season. U sub, parts, trig, whatever, could tell you how to integrate it. Right, so be ready to do that on tomorrow's quiz, along with the stuff from last Wednesday and Friday.